Welcome to Study Loop.
Hi there. So for this problem, we need to determine the potential at different distances from the center of a sphere. And this sphere is has a charge of 3.15 nanometers and nanocoulombs, and it is distributed uniformly over the surface of a metal sphere and has a radius of 24 centimeters. So, and when we have a charge conducting sphere, it is known as a sphere in which all the charges are distributed on the surface of on this sphere. So in this case, because we have a positive charge, we are gonna draw positive charges on the surface of this sphere. So, having that in mind, um, the electric potential inside this charge conducting sphere remains the same. The electric potential inside a charge conducting sphere is equal to the electric potential at the surface of the sphere. So, no matter where we measure the potential inside the sphere, it is always the same as the one in the surface of this conducting sphere. So we need to have that into account when we are going to obtain the potential field inside this conducting sphere. So the first um, question for this problem is to determine the potential to a distance of 48 centimeters from the center of the sphere. So if the sphere measure has a radius of 24 centimeters, we want it like outside because 48 is just greater than 40 like 24 centimeters, which is the radius of the sphere. So for this first part, we need to calculate when art is equal to 48 centimeters. So when we are dealing with a sphere, a charged sphere, if we are going to obtain the electric potential at a point outside the charge conducting sphere, then it is just expression for a point as charge, that is this expression where k is the Coulomb's constant, and Q is the charge, the complete charge, because we are enclosing all the charge, and R is the distance we're gonna call capital R. So in this case, we know that the value of the constant is 9.9 times 10 to the 9 Newton per meter square over Coulomb, and the charge is 3.15 nanocoulombs, and the distance is, we need to pass this into meters, so we know that we need to divide this, and we're going to obtain that this is 0.48 meters. So we put this in here. The potential is then 5.63 times 10 to the 6th. Oh, I think I made it. Okay, no, so it is like oh no, it's not this value, is 65.63 volts. So this is the potential at that point. At point B, as I already told you, we are R is equal to 24 centimeters. So that corresponds to the surface. In here, the surface of this conducting sphere. So to obtain that, we just simply need to use the same formula as before, but using the radius of the sphere, because that's where we want the potential. So the same formula. I'm gonna put this like Q, capital Q. And in this case, the only thing that is changed in this case is the value of the distance. The charge is 3.15 times 10 to the minus 9 coulombs, because that's nano, and the radius is 0.24, because this in here is the same as 0.24 meters, and meters in here. So putting this into the calculator, we obtain 131.25 volts. So at the surface of the sphere, this is the potential. And finally, we want the potential in a point 12 centimeters from the center of the sphere. So it is something like in here. This is R, and we want the potential there. So as I said in the beginning of this problem, the potential in any point inside the unconducted, a conducted metal sphere is the same as the one in the surface of the sphere. So we will have that the potential at the surface, calculated in the centimeters, is the same as the potential inside the sphere. So we just simply gonna put in here that the potential at this point is just the same as before, 131.25 volts. And this is because, the charge in this metal conducting sphere is just on the surface. So we don't have any other distribution of charge, just that in the one in the surface. And it turns out that is the same as in that point. Thank you.